So from previous lectures, for calculating the hydrostatic force on submerged bodies, we calculated how we can find the force value. So we had this F net value given by this formula rho g HCA and the centroid, and then we also found the center of pressure value, the coordinates for the center of pressure, yp and xp, right? So now let's say a question is given to you that you have a curved surface like this, which is again immersed in this fluid. Okay, this is immersed in a fluid, and again this is basically your air, this is your fluid. Okay, with density, let's say this is the density is rho. So the density of the fluid is rho. Let's again assume that this density, the fluid is incompressible, so the density is not changing with pressure. Okay. So now the question is, can we use the previous analysis to find F net and center of pressure on these curved bodies which are submerged in the fluid? So this is the question. So what is the answer? So can I just say that this F net would be equal to this value, which is rho g hc times a, rho g hc times a, and xp and yp are the coordinates for the center of pressure? Can I say that? The answer is no, we cannot. And why is that so? Let's understand that. So the previous analysis, what we had was, we had an object, we had this object, the object from the side view, from the edge view was looking like this, and actually if you see from, let's say, this side, then the object was actually of some arbitrary geometry, but was in such a way that the area vectors of this object, so this is the area vectors for this object, they all pointed in one direction, right? They all pointed in one direction, and we took some area vector, dA vector, and found the value of the force dF vector on it. So this was my pressure, okay, and this was the dF vector, that the force value that was applied on this elemental area because of the pressure of the fluid, right? Okay, and then what we did was we simply integrated dF, right? Now if you think carefully, this force is a vector, and in this case what happened was all F vectors were in one direction. So if you just think about, let's say this is dF1, this is dF2, this is dF3, and so on. So what we had was dF vector, dF1 vector plus dF2 vector plus dF3 vector plus so on was my total F vector, right? So we can just simply write this as summation over dF vector. We simply wrote it like that. Since they all pointed in one direction, the concept of vector was not important. Okay, so what we can in this case what we did was we simply took the magnitude, integrated it, and then we can simply just give a direction. So what would be the direction in that case? The direction was z hat. Sorry, the direction was k hat. Okay. Now in this case, what happens? In this case, we cannot do similar. We cannot just take all the vectors in one direction. Just let's understand here. So if you see the pressure would act normal to the surface, so and will increase with depth. So the force vectors would look something like this. So it would look like that, this would look like this would look like this, and this would look like that. Okay, so you can see clearly that this force vector and this force vector and this force vector and this force vector, they all have different directions. So we cannot simply integrate over df. Okay, correct? So that's why we cannot use this formula for F net, this formula for xp yp to calculate the force value and to calculate the center of pressure. So what we will do for such cases, let's understand that. Let's draw the surface again. So this is my surface, curved surface. Okay, now to solve the problem, we'll make two hypothetical, not actually two hypothetical surfaces, but we'll make surfaces like this. So these are my hypothetical surfaces, or in 3D this would look like this. So this would look like this in 3D. So what we have done is, so let me just draw it in black. So this part was my actual curved surface. Okay, now what I have done is I have created extra surfaces. So I have created this surface, then I created this surface, then I created this surface, and also one surface which is this part, this one. Okay, so I have created all these surfaces so that this now becomes a closed object. Okay, now why are we taking closed object, that would be clear in during this derivation. Okay, so briefly telling you that then we can use the divergence theorem, because we can use divergence theorem only for closed objects. So we can then we'll use the Gauss divergence theorem to convert from surface integral to volume integral, surface integral, to solve this problem. Okay, so that's why we have created hypothetical surfaces so that we can close this surface. So I hope you understand what a closed surface would mean. So closed surface, let's just give a simple example on a closed surface. So if I just search closed surface in Wikipedia, I'll get these kind of images. So these are the closed surfaces and these are the open surfaces. So what is the difference between them? In simple, for a layman, I would say that for surfaces whose inner part you cannot see, those surfaces would be termed as closed surfaces. So let's say there is a ball. Can you see the inner portion of this ball? The answer is no. So then this is a closed surface. So this is a torus. Can you see the inner portion of this? No. Then this is a closed surface. This is a cube. Can you see the inner portion of this cube? No. So then this is a closed surface. Then these are open surfaces. So let's say this is some hollow. So let's say you have taken a cricket ball and you have cut the cricket ball from the center of the cricket ball. So now can you see the inside of this cricket ball? This inside portions you can see? Answer is yes. So then this would be termed as open surface. This would be termed as open surface. Okay, I hope this concept is clear to you. Okay, then let's come to our question. So this is the question that we want to answer. So we had a curved surface and we want to find the force acting on this closed surface. Okay, and we just argued that we cannot use the previous analysis to find the force value. Okay, so now to solve this problem, we made some imaginary surfaces so that our surface, our given curved surface becomes part of a closed surface. Okay. Now let's mark the surfaces as S1, S2, S3. So let's say this surface is S1, this surface is S2, this surface is S3, and this surface is S4, and this surface S5. Okay, so if you just see in 2D, this would be S4, and the surface behind this S4 would be S5. Okay, is that clear? All right. Now the total force on the surface S1. Okay, let's write it with some other color. So on surface FS1 can be written with this trick. So we can write this as Fs1 plus Fs2 plus Fs3 plus Fs4 plus Fs5 minus all this Fs2 minus Fs3 minus Fs4 minus Fs5. So just adding and subtracting the same thing will give you Fs1, right? Okay. Now what is Fs1? Fs1 would be minus n hat p ds integral over S1. So is that clear why negative sign is there? So negative sign is there because, so let's just understand this with some example. So if this is your surface and let's say p vector is going like this, okay, and the area vector would go like that. So let's say the normal area vector is n hat. So what would be the force value? The force is acting in the direction of p vector, right? Okay, so actually pressure cannot be given as a vector. So p is acting like this, and the force should be acting in the direction of pressure and not in the direction of n hat. So that's why PDS minus n hat will be the force. So force is acting opposite to n hat. So it's going in the direction of pressure and not in the direction of n hat. It is opposite to n hat. So that's why we have taken negative sign here. Okay. Okay. So Fs1 would be this one. Similarly, Fs2 would be minus S2 n hat PDS, and similarly Fs3, Fs4, Fs5, and okay. All right. So now if you see Fs1 plus Fs2 plus Fs3 plus Fs4 plus Fs5, this can simply be clubbed as integral over the surface S, where surface S consists of S1, consists of all these surfaces S1, S2, S3, S4, S5. This becomes a closed surface, and we can simply write n hat p ds minus integral over, now we are writing these terms. So this would be not S1 but this would be S2 n hat PDS minus S3. So this is used for a closed surface. Okay, we write this integral when the surface is closed, and this integral when the surface is not closed. So let's write this as, then we have S4 n hat PDS minus S5 n hat PDS. Okay. All right. Now let's define the normal vectors n1, n2, n3 for S2, S3, S4. So let's define the normal vector on this surface. Let's define with some other color. So this is, let's say, n2 hat. This is, let's say, n3 hat, the normal vector for this surface. Similarly, this will be n4 hat and this will be n5 hat. Okay. And let's define the coordinate axis. So let's say this is y, this is z, and from y cross z we can get x. So y cross z will give you x into the plane. So let's say this is x. Okay. So from here we can see that n2 hat is nothing but j hat, n3 hat is nothing but minus k hat. And what would be n4? N4 would be opposite to I hat. So just write it down. Let's just write it down. So what would be n1? Okay, n1 is still not that straightforward, but we can write about n2, we can write about n3, we can write what would be n4, n5. So what is n2? N2 is pointing in the direction of y-axis, so this will be simply j hat. What will be n3? N3 is pointing in negative z-axis, so this would be minus k hat. What would be n4? N4 is pointing out of the board. Okay, so but x is inside into the board, so that's why this will be minus I hat, and n5 is I hat. So we'll just replace these n vectors with the non unit vectors. Let's just replace them. So for n2 my normal vector was j hat. For s3 my normal vector was minus k hat, so this will become this like that. Then for s4 the normal vector was minus I hat, so this will become like this. And for s5 this is I hat, so this will become like that. Okay, now from the symmetry of this problem we can say something about s4 and s5. From the symmetry of this problem we can see that same force would act on s4 and same force would act on s5 because their geometry is exactly the same. But these force vectors, since the area vectors are in opposite direction, the force vector would also be in the opposite directions, right? And that's why from this part also it is clear that one is positive, the other one is negative, so these two terms would cancel out and we'll be left with these three terms now. Okay, now to simplify this expression we will use the Gauss divergence theorem. So let me just state the Gauss divergence theorem. So Gauss divergence theorem. So the theorem states that for any closed surface, so let's say this is your closed surface and there is some vector field, let's say there is some vector field A vector, then this theorem states that the surface integral of A vector can be changed with the volume integral using the divergence of that vector field over that on that body. Okay, so this is the statement of divergence theorem. So this holds true only for closed surfaces. So this surface has to be a closed surface, otherwise you cannot use Gauss divergence theorem. Okay, all right, but in our integral we actually don't have the vector field. Okay, but we can use the corollary of this statement to simplify this expression. So what is the corollary of this statement? So the corollary is f, so this would be n hat ds is equal to grad f dv. Okay, this is the corollary of this Gauss divergence theorem. Alright, now we can see here, and this f is a scalar. The same thing, this can be identified, okay, sorry, this is s. So this expression here can be identified with this expression, right? So then we can use this corollary to write this, to write this term in terms of the volume, the gradient of this pressure. Let's just write it. So this will become, what this would become, this would become simply grad f, grad of p dv, right, integral over volume minus s2 j hat pds plus integral k hat pds s3. Okay, so let's briefly see what we have done till here. We wanted to find the force on this curved object. Since the previous analysis cannot be used directly, we created some hypothetical surfaces so that this surface becomes part of a closed surface, and using simple analysis of writing force in terms of pressures and knowing the values of this unit vectors, so we wrote n2, since it is in the direction of y-axis, n2 becomes j hat, n3 since it is in the direction of minus z-axis, this will be minus k hat. Similarly n4 and n5 were written. Okay, then we, using the Gauss divergence theorem, we wrote this surface integral in terms of the volume integral. So if I see from here, I think I have done some mistake over here. So if I just see, then fs1 plus fs2 was actually minus, okay, because of the reason I just gave during this derivation. Then I think I have done another mistake here. So for s2, this is j hat. All right, so I think, yeah, okay, so this becomes minus. Now if you remember, when we were deriving how pressure varies for a cubical fluid element, we derived this expression that grad p is equal to rho g hat, rho g vector. So this was the expression we derived there. So we will use this expression here. Okay, so we can just write this grad p as rho g vector. So this becomes minus rho g vector dv, and where is this gravity acting? The gravity is acting the positive x-axis, z-axis. So we can just write this g as g k hat integral. So this becomes k hat dv minus s2, this is volume v, j hat pds plus integral over s3 k hat pds. Okay, all right. Now since this rho and this g is independent of this volume element, so that's why we can take this outside of the integral, writing this as minus rho g. Again, k hat is also independent of the volume, and this dv, the integral of this dv will simply be the volume of the object, right, minus s2 j hat pds plus s3 k hat pds. Okay, I can write this j hat and k hat outside, so let's write it j hat and k hat. Okay, all right. So now what are these s2 and s3? s2 is this surface and s3 is this surface, right? Now if we see, this s3 is a horizontal surface, so the pressure would not change if you take different area vectors on this s3, right? So that's why on this s3, this pressure is independent of the area vector that you have chosen. Okay, so then this pressure can be taken outside of the integral. Okay, and what will be that value? That value will be simply the height, the depth of this surface, times rho g, right? Simply the hydrostatic pressure. So we'll write the depth h rho g integral ds. Okay, now what is this integral over ds? So the ds is somewhere here for this S3. Okay, and the area total integral over ds would be simply the area of this surface, right? Or if you see in 3D, the area would be of this surface. Okay, area of this surface. All right, so let's say that area is S3, the area of this surface. So we can just write this as S3. Okay, this becomes S3. So if we just club the terms for k hat, this would become h rho g minus h rho g times S3 minus rho g times volume of the object k hat minus integral over S2 j hat outside PDS. Okay, now we can again just take rho g common from both these terms. So rho g would look like this. So this expression would look like this, right? Now think carefully, what is HS3 minus V object? So let's draw the curved object again. So this is my curved object, right? Okay, just let me just write it in this side. So this is my curved object, this was my fluid. Okay, now what is HS3? HS3 is simply, so this was my H and S3 was the area of this surface. So HS3 is this much volume, right? Okay, and what is the volume of the object? This is the volume of the object, right? So what would be HS3 minus volume of object? This would be nothing but the volume of this part, right? And what is this volume? This volume is simply the volume of fluid. So this term, let's just write it here, HS3 minus V object is, now if you multiply with rho times g, this becomes the weight. So let's just multiply this part as well. So rho g into HS3 minus V object would be the weight of the fluid above the curved surface. Okay, so this is simply the weight of the fluid. So let's just write it like W, and this is the weight minus J hat PDS integral over S2. Now what is this term? Let's understand this. Now what is S2? S2 is the flat surface, and we have already done analysis for the force on such kind of flat surfaces. And what was the force value? The force value was, so minus integral PDS will be the force value, and that force value we know this is equal to H centroid rho g times the area of that surface, right? So in this case, what would that be? It would simply be the the depth of the centroid for the surface S2. Okay, so let's say this is the depth of the centroid. Let's say this is HC. Okay, for this S2. Now what is S2? S2 is simply the projected area of surface S1 on this plane. And what is this plane? This is XZ plane. Okay, so this HC, okay, just let me just write it firstly. So this is equal to W minus J hat. Okay, minus would become plus, since now I am just writing the value of the force. So this will become HC rho G times area of this S2 surface, where HC and AS2 are, so this is the depth of centroid and this is the area of surface, and they belong to the projected area of curved surface, projected vertically. Okay, right? Let's see if there is any mistake or not. Now checking with the literature, it shows me that this should be plus J hat integral PDS. So I think I have made mistake in this J hat PDS. Let's just check this. So we had FS1, FS2, we just wrote it like this. Then FS1 was minus and had PDS, FS2 was this one. So this would become minus over n hat, minus over n hat, so this was correct. Then it was minus FS2 and FS2 was negative itself. So this should be overall plus. Is it correct or not? Just think about it. And also this is positive Z and N3 is in the positive Z direction. So then this is plus K hat and not minus K hat. So just let me just for clarity write it again. Let me just write it again. Okay. So I hope this term is clear. Then what we have is plus integral, since this is minus and fs2 was itself negative, so this will be plus integral over s2 and had pds plus integral over s3 and had pds plus integral over s4 and had pds plus integral over s5 and had pds. Okay, and for s2 the normal vector was n2, so write n2. For s3 the normal vector was n3, this is n4, this is n5. n2 hat, let me just again check whether I have written this correct vectors or not. So n2 hat is in the positive y-axis, so this is correct. n3 I just corrected it again, so n3 is actually in the positive z direction, that's why this should be plus k hat. n4 was in the minus x-axis, so this should be minus I hat and this should be plus I hat. Okay, so then we can just replace this. So let's replace this. So by looking this thing, so n2 is, what is n2? n2 is j hat. So j hat, what is n3? n3 is k hat. So let's write k hat for this. n4 is minus I hat, so this is minus I hat, and n5 was plus I hat, so this will be plus I hat, and these two terms would cancel out and you will be left with these three terms with, so this is positive and this is positive. Okay, so that's why this should be positive. Okay, so this positive was already there, so this term is correct, this term is correct, this should be positive, so everywhere I have to just replace this negative sign with a positive sign. So this will be positive and this will be positive. Okay, now integral over PDS, this gives me the force, but that force is not in vector, so that's why this won't change the sign. So this positive would be positive, and we have to just write the magnitude of that force. So this was the magnitude of that force. Okay, so that's why this will remain positive, and this will be hc rho g times as2. Okay, so again the definitions would be the same. hc is the depth of the centroid and as2 is the area of the surface. And this w should come with k hat. Okay, so this was just the magnitude w, so this should come with k hat plus k hat w plus z. Now let's say you have done this derivation and you want to be sure that whether you have written the right signs for the force vectors or not. So you can just check this with a simple trick. So you had this surface, and these were the force vectors on it. So the force vectors were like this, like this, like this, like this, and like this. Okay, so all the force vectors are being applied like this, nearly like this. Okay, so if you resolve these force vectors, this would look something like this, and my coordinate axis was, so this was y, this was z, so this was y, this was z. So my force vector that I should get should be in j hat with some magnitude plus k hat with some magnitude, and this is exactly what we get over here. So this is k hat with some magnitude and plus j hat with some magnitude. So you can be sure that your signs are correct. You won't do, and you have not done any mistake like what I just did over here. So with one mistake I got the final answer wrong, but still if you want to see whether you have derived the correct answer or not with correct sign conventions, you can just use this trick. Okay, all right, so let's just briefly summarize the lecture. We were given a curved surface submerged in a fluid. Okay, and we were asked that what will be the force on this curved surface on this curved surface from one side. So if you think that if you only take one surface and you find the net force, that force will only be because of the weight of this surface. Is that correct or not? Because the same kind of pressure force would act from this side, right? It would be something like this. So that's why in most of the problems you will be given that on one side of this surface there is air and on one side there is a fluid. Okay, so then only we can use this analysis to find the force value. Okay, so let's say this problem is given to you Then what, now the question is, what is the force applied by the fluid on this surface? So how will you find this value? So you will firstly find the weight of the fluid which is above this surface. Okay, let me just mark it with some other color. So the weight of the fluid which is above this curved surface, so the force value, the force on curved surface is equal to, so firstly to so the trick is, you see the fluid and what would be the pressure force that would be acted by this fluid. So if I see this problem, the pressure force direction would be somewhere like this, and resolving this would give me this. Okay, just let me just mark it with solid, and this is dashed. The resolved parts are in dash lines, and so whatever the coordinate axis is given to me, let's say the coordinate axis is y and this is z. So I will just write that this force on a curved on the force by the fluid on the curved surface would be, so would be j hat times the magnitude of the force along j hat plus, now this is acting in plus k hat direction, so plus k hat times the magnitude of the force in the z axis. Okay, now what are these magnitudes? So this and this, so this is simply the weight of the fluid just above this curved surface. Okay, so this, let's call it B and let's call it A. So B is the weight of the fluid above curved surface, and A is, it is equal to the pressure force acted on the centroid of the projected area, projected vertically. Okay, so the pressure force acted on the centroid of the flat projected area. Of course the projected area would always be flat, but still let's write it flat projected area, so that it is known to you that this force value would be given by hc rho g times A, where A is the area of that projected surface, rho is the density of the fluid, hc is the depth of the centroid of that projected area. Okay, all right. So this is how you will find the force on that curved surface. And please note that when you are writing the weight of the fluid above the curved surface, it does not mean that this has to be the fluid above the curved surface. So it can be the hypothetical weight of the fluid as well. So let's say the curved surface is not given like this, but the curved surface is, let's say, given like this. Okay, and let's say you have the surface, you have surface like this. Okay, let's say the surface is like this, and this is my fluid inside the surface. Let's say the container is like this and the fluid is filled in this container. Now you have been asked, so let's just mark this as AB. So you have been asked to find the force on this surface AB, the force on the surface, just on the surface AB. Okay, so in this case you may think that, oh, there is no fluid on top of this surface, so that's why this weight of the fluid should be 0 and this term would cancel out, but this is not the case. Okay, so this weight is actually can be the hypothetical weight of the fluid as well. So how will you solve this problem? We will solve this problem by taking the weight of this hypothetical fluid on top of this surface. Okay, so this, the weight of this fluid plus, so this term will be calculated like this, and to calculate this term we'll just take the projected area, we'll just consider the pressure force on the projected area projected vertically. So my vertical projected area would look like this. Okay, and by knowing the dimensions I'll know what would be HC and what would be the area of this projected surface, and I will know this term capital A. Okay, so I will know B, I will know A, and I will be able to calculate the force value on this curved surface. But this time, since the fluid is like this, the pressure applied by the fluid would be something like this. Okay, right? So to know the vectors beforehand, you can just simply resolve this pressure force direction or this pressure force vector just like this, and let's say the coordinates is this the same coordinates we used here. So let's say this is Z and this is Y. Okay, so what would be the directions? So this is along minus k hat and this is along minus j hat. So A times minus j hat and B times minus k hat. Okay, so this will be the total force on this for this curved surface. All right, so you will know that firstly you have to know what is the weight of the fluid, or maybe the hypothetical weight of the fluid above this surface. You have to project the area, get the value of HC and capital A for that projected area, calculate the magnitudes, and then for vectors you simply resolve the pressure force and get the value of this unit vectors. Okay, so this is how you approach the problem for the curved surfaces. Okay, yeah.